me to start sharing and presenting. Thank you very much.
Hi, everyone. Thank you for the very kind, very detailed introduction. I hope everyone can hear me. And
Yeah,
also,
yeah.
I will look at the other screen, so, probably I will not face at the camera. And well, I think the sound is fine, so I will start. Hopefully we can finish, or I can finish my talk within 45 to 50 minutes, and then we will have some time for the Q&A. Okay? All right, so this is full screen mode.
Yeah, it's
Okay.
yeah.
All right, so I will start my talk today. The title, as Prof. Reddy just mentioned, is the methane emission from landfills, and especially about the underestimation of these methane emission from landfills worldwide. So I will talk through the background and then also our recent progress and etc. Let me turn the highlighter to the red color. Just as a for your FYI, for your information, the most of the results that I'm going to talk about is basically published on this paper. It's a recent paper and it's Nature Sustainability. So we put a lot of effort in this paper and we are pretty happy and proud about the results. The title is basically the same title for the paper and also for the presentation. So let's start. Like Prof. Reddy said, it's solid waste is a major problem and it's very much at the heart of this discipline, geoenvironmental engineering, right? So I will just very briefly show you or mention again what is the major problem about municipal solid waste, MSW. Essentially, this is about the generation and disposal, right? So here I want to show you mainly two figures briefly. They are taken from one of the latest official report from the UN meaning the United Nations. So it's a global, worldwide report talking about the latest data or latest status of the solid waste problem worldwide. So what we can see from the left figure here is a projection, first of all, the current global waste generation per year, and also the projection to the future by 2050. Okay. I think he's
Yeah, go ahead. Go ahead.
no worry. Yes. Let's first look at the global solid waste generation per year, right? We are now at 2024, so roughly at this time, 2020, let's just pay attention to the unit on the y-axis. It's actually in billion tons. So nowadays, every year, all the people in the world are generating around 2 billion tons of solid waste every year. That is a huge number, right? And then if the world goes as the way it is, by 2050, just 30 years later, we will almost double the solid waste generation per year to around 4 billion tons every year. That is not taking even into account the waste that we have to dispose of in landfills and etc. Just every single year, we have this huge amount of solid waste generation, though. So that is a major problem, and that's why many people in geoenvironmental engineering and also geotech environmental engineering, we are worried about this problem, and we are also trying our best to deal with the problem. The right figure again just supports this idea by showing that the waste increment both come from GDP growth and also population growth, and that these growths are kind of inevitable, and then they are desired by the government, by the different countries. So in other words, this waste problem is going to persist in the long term because the countries want to develop, people want to grow their family size, country want to grow their population size and GDP size, right? So all these will result in increased solid waste generation. So that is a major problem we are facing now, dealing with the solid waste problem. Then just briefly, let's talk about how or different countries worldwide are dealing with this solid waste problem. Again, I'm showing the figures from two very famous reports. One is the World Bank report. I believe all of us know this, What a Waste report. And then the other one is from the UNEP, the latest one. So what we are seeing here is, obvious, like before the the seminar started, we were talking about Prof. Reddy is asking people to, type in where are you from. I saw that many people are from US, but obviously there is a major portion of people coming from South Asia and Southeast Asia, or even East Asia, meaning China, India, and etc. Right? So we have quite different ways of dealing with solid waste. But here, if we look at the top left figure here first, the US obviously is a high income country, and then, most of the, or half of the waste almost, are sent over to landfills, which is this green color here. Even for the upper middle income countries, I believe, which includes South America, and then also China is recently recognized as the upper middle income country. 50% of the waste is landfill, right? But now we start seeing this blue color. What is this blue color? This actually indicates waste goes into open dumps. Open dumps are, in other words, dump site or unregulated landfills, right? So the waste are stored in the environment, but then they are less controlled or not sanitary, not sanitarily disposed of, meaning that they are even more damaging or detrimental to the environment. So that is one key problem now we are facing, is that we have huge amount of waste that we need to deal with. And in the same time, the waste are either, or most of the waste, a lot of the waste are stored in either landfills or dump sites. This problem is even more pronounced, in the lower middle income and low income countries. As you can see, for low income countries, even 90% of the waste is dumped to the environment without proper control. And when I was studying in the US, usually and also when we look at research papers for waste management and etc., right? People are always talking about landfilling, recycling, incineration. Sounds like, we're all talking about all these high-tech solutions, but well, it's partially because the low-income countries, it's kind of, we call it the unnoticed majority. I did a very quick calculation. Low-income and lower middle-income countries, they actually make up of half of the world's population. And the waste generated in all these countries are mostly dumped in dump sites. So that is a major problem as well, meaning the waste are not even properly controlled. The lower right figure shows the similar idea, meaning that we can see the controlled waste, which are in the shallow color, versus uncontrolled waste that are in the solid or deeper color, and then their increasing trend in the future. So overall, the message I want to give you on this page is that we are dealing with waste mainly by putting them to the environment. And then even if they are sanitary landfill, we are facing this problem called methane generation. If the waste is dumped in dump sites, it's even more problematic, and we are facing even more methane generation. So now let's move on to the next slide, or basically the key topic of my talk today, that is methane generation from both landfills and also dump sites. All right, so here, basically, we will start talking about methane. Methane, we all know, is a very strong greenhouse gas. Some people say it is around 80 times higher than CO2 in terms of greenhouse gas potential. Some other people say it's around 30 times. But anyway, it's a very strong greenhouse gas, contributes to about 1/3 of all the global warming effect. So now, or recently, many people there is a very rapid growing interest in methane, especially because, well, we know that methane is very strong, well, methane contributes a lot to the global warming, and then just after CO2. Many people have realized the problem of CO2, so now they are thinking, okay, we need to also tackle the problem of methane. Methane mainly comes from two sources. One is, as you can roughly see on this photo here, one is the oil and petroleum sector. This is actually not our problem, just to mention. The other major source, like it's mentioned here, or I will talk about later, a bit later, is basically from solid waste management. As well, this, by the way, this front page is actually a science paper published just last year talking about solid waste and also greenhouse gas emission. So I just want to show you that, many people are paying more and more attention to this problem, methane from solid waste generation. And basically we cannot imagine 10 years ago that someone can publish on Science or Nature about solid waste management, right? But now you can see that there are quite a few papers appearing on these, very comprehensive, top-notch journals talking about solid waste management, their mitigation and management roadmaps, and etc. So indeed, many people are start to realize that it is a major problem, and hopefully my research that I'm going to introduce later on will convince you a bit more and also give you a bit more background and in-depth insight into this problem. So like I said, all the countries start to take action as well. There is a major action called the Global Methane Pledge. It is basically an international pledge or action that many countries signed, saying that they should look into the sources of methane emission within the countries and then think about how to mitigate and lower the emissions. It is a major global or international initiative. As you can see now, more than 150 countries have signed this global methane pledge, as also see here during COP28, which was last year. More than 150 countries, they have signed this pledge. And by the way, China and India, they are in a similar initiative, not the same one, but called Global Methane Action Plan or something. So most of the countries, they are aware of this problem and start to look into this. And well, that also motivates me to look into this problem again. By the way, when I was doing my PhD almost 15 years ago, I was also looking at methane emission from the solid waste. So it's kind of a perfect time for me to take another look, fresh look at this problem. All right, so then, I was reading through all these news reports, announcement about the methane emission from waste, and then I basically gather a few key numbers. The first one I just talked about, around between 2 to 3 billion of tons of municipal solid waste is generated every year globally, right? Then the number here shows about 50 tetragrams TG of methane is generated every year only from municipal solid waste. This is 10 to the order of 12, so it's a huge number. And it accounts for about 10% of all the anthropogenic methane emission on Earth every year. So it is, well, lower than the methane emission from the oil and the petroleum sector, but waste is kind of unnoticed or unrepresented field, right? We have a small group of people, but actually this methane emission problem is pretty big compared to the size of the discipline and then the researchers, right? So indeed, I think it's worth exploring further. So then I also look at what are the current knowledge about methane emission from the waste, and then found, basically I summarized the data into this figure. On the x-axis is showing time from year 1990. And the y-axis is the estimation of annual methane emission from waste alone from other countries. So I did find a few official, or I shouldn't say official, but pretty comprehensive sources showing the amount of methane emission from waste alone. What you can see here is that, they show the increasing trend, which is not surprising. And then the total amount is, more or less 50 tetragram TG per year. Then I realized, okay, if I plot the uncertainty range, for example, if we look at this blue part here, this blue curve, right? The uncertainty range is reported by this database. By the way, this EDGE database, I think, is also supported by the United Nations. So they show that the total amount of methane emission from waste is a bit more than 50 kg per year, right? But then the uncertainty range arrow bar is almost the same as 50, as you see here, right? So basically, we're saying that methane from waste is around 50 kg per year, plus minus almost 25. So the uncertainty range is very, very high. So that is what kind of motivates me or drives me to go further into this problem, is to see first of all, where is this uncertainty coming from, right? Why the error bar is so high? And then later think about how to improve the situation, because we need a clear and accurate estimation of methane emission. Then we can really think about how to reduce the emission, tackle the problem, right? If we have such a large range, basically we feel uncomfortable, and also the policy, the engineered mitigation solutions will be confused as well. So now let's move on to really look at how people are estimating methane emission from waste nowadays. All right. So we basically have two major approaches, the left one and also the right one. The left one here is what we call conventional approach, or bottom-up inventory method, which is recommended by IPCC. IPCC, is that International Organization for Climate Change, right? So they are recommending a very straightforward method. By the way, it's also very similar to US EPA's method. It just says that we can estimate methane emission from waste, from landfills, using this first order decay model. The first order decay, which is basically one line. We can summarize most of the stuff into one line. It says that the RCH4, the rate of methane emission, is equal to L0 multiplied by W, K, and the first order term. So L0 is the methane generation potential here. Basically, it's just the total amount of methane that can be generated from per unit of waste, per kg of waste. Liter of methane per kg of waste. So that's just the amount, right? It's very quite easy to measure and obtain. And then the other number is also straightforward, waste disposal mass, W, in kg or in tons for each landfill. But then the trick, or I realized that the confusion or the uncertainty mainly comes from this K value, that is the waste decay rate. Because this decay rate, by default, there are a few default numbers given by IPCC. And then these numbers later I will show that are not very precise. But anyway, this is the current approach or mainstream approach. Mainly, in many countries, this I think is, let me kind of pull sideways and say that I'm really thankful for Prof. Reddy to organize this seminar, because I see many people, from the different countries, and especially, different parts of the world. And I believe that you more or less will or have heard about this method, because this is a really straightforward method for not only, America or Singapore, these high-income countries, but for low-income countries, it's a very useful tool. It is because, it's low cost. It's very kind of dirty and quick, meaning that you just need to use the default values from IPCC's handbook and then plug in the waste disposal rate. Then you can estimate your methane emission from the landfill. But obviously, you can imagine now we are talking about the low accuracy problem. If we are using all these default values, basically we have this very simple and easy equation. Then we start to question, right, if it's accurate. The answer is no. Methane emission nowadays, some of the recent papers published and found that methane emission from landfills in the US and also in India, Argentina, and etc., a few other countries are largely underestimated. And the methods they use, for example, these two papers, by the way, these are also very famous, published on very famous journals, Science Advance, and very recently a science paper. These people and these papers said that the landfills in US, high-income country, and also in Argentina and India, mid-income and low-income countries, no matter where they are, methane emission estimated from these landfills are way lower than the actual values. And they use a method called atmospheric inversion, or just simply speaking, satellite method, to capture the image of methane emission, methane plume, and calculate methane emission flux. They show that all the landfills, the methane emission estimation are way lower than the actual values. But well, then, okay, I'm thinking, yeah, sounds like we don't have a problem anymore. If they can use satellites, then every problem should be solved, right? Then I realized, or people also realize that, satellite image is very high cost, although it's very high accuracy, right? This means that, it's not possible for all the landfills to be analyzed by the satellite and then to be even scanned by the satellite. Not even US can support this or afford this, right? So then I start thinking about my own research. Basically, how to improve this IPCC method to make it more accurate while not mobilizing satellite all the time. So that is basically the background of my and motivation of my research. Now I'm going to move on to talk about my methodology. All right. Yes, here, first it's my research is then broken down into three major steps. The first step here is a data collection. Basically, I want to know how many landfill sites have been surveyed by the satellite or some of the on-site methods using flux chamber or the sensors, because that's kind of the basis. We want to know how many landfills and their methane emissions. Then I will show you briefly a method to improve the K value. Remember the K value I just mentioned in the IPCC handbook, because I think it's still valuable. IPCC's handbook or IPCC's method is still very easy to use, easy to apply to most of the countries. So instead of completely get rid of this method, I want to improve the method so that it's still easily usable, accessible, while it is also more accurate than before, and it can agree better with the satellite data. So this is about methods development and verification, validation. Then eventually I will also show one page about the third step, method application, meaning extrapolating our method to globally to all the landfills worldwide. Okay, so then let me show you the first step of my research, that is data collection. Basically, this world map is showing you, or I should say that all these circles on the world map are showing the places with available data. And why the place is important is because, these different places, they generate waste with different composition, right? So in basically no group or no researcher can go to all these different places in the world to collect their waste and test in the lab. So in the sense that we do have to rely on the data from the literature. It's called a meta-analysis, where we just get data from the literature, do the analysis properly, and then we can get some insight into the problem, right? This meta-analysis, I think nowadays is very common and useful in ecology, global environmental science, climate change, and etc. So I basically adopt that method to our waste research. Okay, so what I'm showing here is all these different dots, circles, meaning places with waste degradation tests and waste degradation tests leading to K values, right? Again, we are focusing on this K value here. K is the waste decay rate. In total, we have about 200 field measurements and about 80 laboratory test results. So these will serve as the database that we will look into, and then later on improve the K estimation. Okay, the red circles represents the field measurements. The blue ones are the lab measurements, and some of the light blue ones are actually the satellite image surveillance data. So you can see that we have obviously North America very nicely represented, Asia, South Asia, East Asia, and also part of the Europe, and there are a few other places worldwide. So we think that, okay, the database or all these data are fairly representative of the global situation. Also, we are missing the data from Africa and then from a few other places. But well, let's start the analysis and see what can tell us. Okay, so then we first did a statistical analysis, looking at all these K values, right? We first separate the K values into field measurements and also the lab testing. This is now we are looking at the top lab figure here. So the first thing we can note, and x-axis are two groups. field measurements, lab testing, and then the y-axis are the values using either the left or the right axis. The first thing we can notice, obviously, is field measurements, the K values are much lower than the lab test. But we think it's reasonable because in the lab we accelerate the waste degradation, so the K value, the decay rate is much higher. In the field, it's lower. So yeah, this makes sense. And then this is just a side observation. But what's more interesting is, now we are for the top right figure here, we are separating the field K values. Now we are only looking at the field K because these are the real K values, right? From all the landfills. The field K values, then we separate them into two groups. One is annual temperature higher than 20 degrees. The other is annual temperature lower than 20. Why we separate it as this way is because this is according to IPCC. IPCC says we have tropical countries and also the non-tropical countries. Then you just use 2K values to represent the landfills in these two types of countries, two groups of countries. But in reality, if we see or check, compare the K values, right, you see there's no significant difference. This is basically saying that IPCC's guideline for choosing K value for landfills is not that good. I mean, well, it's kind of this leave as a question that I will explain a bit later. But well, this is the first question we notice is that temperature, if we only separate temperature into two groups, higher than 20 and lower than 20, then it does not help us in estimating or getting the K value, right? Then the similar observation applies to precipitation as well. If we look at the bottom left figure, you will see that IPCC says if you are in a, again, tropical country or raining country with annual precipitation larger than 1,000 millimeter, then you should use 1K value, higher K value. If you are in a dry country, use a low K value. But in reality, all these field measurements are showing that this separation or this distinction separation is not very meaningful because the K value is not only determined by high or by wet or dry in terms of the climate zone and in terms of the country. So that is another question mark here, right? So now we have two question marks that we need to kind of solve for and improve. The third thing, the last figure we are looking at here is the bottom left one. This actually is not a question mark. So we are seeing here Annex 1 country versus non-Annex 1 country. For those of just for your information, Annex 1 country means the developed countries or OECD countries. And then for those countries, the field K measurements are in general lower than the developing countries, the low-income countries. But we believe this is because the low-income countries, there is a higher amount of organic waste, food waste in the landfills. So they actually have a faster methane generation rate. This is kind of making sense, right? So, okay, from all these data collection and statistical analysis, we found out that IPCC's method indeed is not very accurate, not very accurate, in the sense that the temperature distinction or temperature group and also the precipitation grouping are not accurate. They are not really showing the true difference of the field measurements, right? So then, okay, we say, what can we do to improve this while still, maintain IPCC's framework, use the first order decay equation without, destroying everything and set up new equations, new model that, may not be that straightforward and easy to use. So we say, we think, okay, let's just so-called improve or modify this K value. So here is again, another busy figure. Let's first look at the top part of this figure. So how do we improve the K value while still, use that in the first order equation is we first, after reading all this literature, we know that temperature, precipitation, the rainfall, water content, and waste composition. The fourth one is operation condition. These are the four major factors influencing or changing the K value. But instead of, IPCC's approach by just putting high temperature versus low temperature K, right? So it has a high K and a low K. And then for precipitation, it has a dry K versus a wet K. Instead of this very, crude categorization, we want to uh, put yeah, I'm trying to use another pen which is thinner. We want to actually use two continuous functions to adjust or to show the influence of moisture, precipitation, and temperature on the K value. So that is what we have done based on the database, which contains about 300 different data points, right? So to put it simple, although later on, if you are interested, I can talk more or tell you more about the details. But to put it simple now, our approach is first we use this ternary diagram. By the way, the ternary diagram shows us the waste composition. By picking one point from this triangle, we will get a K value to start with, and then we use this continuous moisture adjustment function and another continuous temperature adjustment function. So these two continuous functions, from these two continuous functions, we can get two numbers. How do we get this? For a specific landfill, we are able to know what is the moisture of that landfill, right? And what's the waste composition of this landfill? What's the temperature of this landfill? So based on the site condition, we can get three values. And then we just simply multiply these three values together to get a new K value called KCMT. CMT stands for composition, moisture, and temperature. So that in the end, we instead of getting one value from the IPCC table, IPCC basically has a very simple table that tells you which K to choose from. Now we are saying that we are taking a bit more, another step further to select or determine three values and then calculate this new K value called KCMT. So this is what we will use later on. But in comparison, then, here on the bottom part of the page, I show a quick comparison between the K value that we modified or we obtained and then the default KIPCC value. These two K values are specific for this landfill in not Bangladesh, Pakistan. Why this landfill is because this landfill has been scanned carefully by satellite images reported in this Science Advance paper. So in this paper, they are saying that the methane emission from this landfill, I believe is actually a dump site in Lahore, Pakistan. They say that the Science Advance papers authors, they said that methane emission from this landfill is twice as much as estimated by IPCC. All right, so 2 times higher than IPCC. And then indeed, if we use our approach to calculate a new K value, it is about twice or 2 times higher than IPCC's value. So basically it's showing you that, our modification approach of K is better or closer to the real measurements, meaning the satellite measurements. Basically, we assume or we consider satellite measurements to be the most precise, right? I think this no one can question. Whereas, IPCC's default value is kind of half of the reality. Yeah, but this is just one case. Although, after calculating this case, we feel pretty good. We feel confident about our approach. But then, we understand or we anticipate many people questioning our method, basically saying that, hey, for this one landfill, you can do a lot of model fitting, right? You can basically make your data nice, make your data beautiful. So now we have to go through the two-step verification process, basically, verify our approach very comprehensively and objectively so that, this method, to show people that this method is really useful and practical. So what is step one verification? It is basically comparing, let me say that we have around, remember for the database, we have around 200 landfills, right? Where we have the field measured K values. This is called KR, K reported. And then we consider these KR values to be the benchmarks or the baselines, meaning they are the most accurate values that we can get for these 200 landfills or dump sites, landfill or dump sites. And then for these 200 sites, because we know where they are, we can also get their site information, including disposal rate, the climate zone, and also the operation condition, right? If it's a landfill or if it's a dump site. So for these 200 sites, we can also get the KIPCC. Again, KIPCC is just by checking the country of the site. Then we can, and also the climate of the site, we can get this KIPCC value. Similarly, as I described on the previous page, we can calculate 200 and 195 KCMT values based on our modified approach, right? So now we have 200 benchmark values, KR, 200 KIPCC, 200 KCMT. Then we compare them. Obviously, eventually we want to show that, our KCMT values are more precise, more accurate than the KIPCC values, the default values. All right, so let's first look at this right figure here. This right figure on the x-axis is showing KR, all these reported values, versus KIPCC, right? So basically IPCC values. Oh, and by the way, why I keep mentioning IPCC values is because even for the Global Methane Pledge, remember I mentioned that it's the major international initiative. For the Global Methane Pledge, they had a long report showing the current methane emission from all the countries worldwide, including the waste sector, right? They are using this KIPCC value to estimate national methane emissions. So this value is important. Many people are using this. Now, well, looking at the right figure, what I'm showing is that, if we compare the reported K value versus the IPCC K value, right? You see that it's basically very poor agreement because KIPCC essentially has 4 values, default values, like I mentioned a few times, based on the country and also based on the temperature and rainfall. They have, and also the income level of the country, they have 4 values. They just say, hey, for America, for US, use, I believe this value, 0.05. And then for like Indonesia or India, the tropic countries use a higher value, for example, somewhere here. But then obviously I want to show this figure to impress you or kind of to show you that, the KIPCC is very, very inaccurate, far from the real measurements, the real values. Also, we are not blaming, I don't want to blame IPCC too much because, IPCC, they have some general guide. It's basically just a general guideline, right? And even in their appendix, they acknowledge that the K value, default values are not very accurate. They are saying that if you have a better K value, a measured K value, then you just use the better value. It's by all means, you should use the measured value. But again, from all these landfills worldwide, by the way, I believe there are more than around currently maybe around 500,000 landfills worldwide. Only 200 landfills have been measured for their K values. So just imagine how difficult it is to measure the K from the site, right? So we still have to use some estimations. All right, and again, the KIPCC estimation obviously is not very good. So now let's move to the left figure here. The left figure is showing our improved K values versus the reported K values, which are basically the most accurate ones, right? You see that the first impression is, all these points are pushed toward the 1-to-1 line, pushed towards the center. 1-to-1 line means that, the estimation is perfect or as good as the measurement. So we want everything to be on the 1-to-1 line. Although, in the end, we can't really make all the data points or all the K values to be very accurate, but at least we show that we are improving based on or from IPCC. At least we are pushing all these data points towards the center, towards the 1-to-1 line. So that is, the first step of our verification, showing that, our method is indeed better than the IPCC's method, while, we are still relying on the site information, meaning that we don't have to go to the site to do the measurement, or we don't have to use very fancy, like hundreds of equations to calculate this K. We just need 2 or 3 equations. So it's kind of still dirty and quick, but better than IPCC. That is our goal for improving the K value. All right, so this is step 1, verification. Then we are close to the end, but then we were thinking, we meaning my student and I, our team, we realized that, the satellite numbers, they are also very, like I mentioned, they are considered as the most accurate values of the landfill emission, right? But then most of the satellite values are showing, well, this is because of the inversion method, because all the satellite or the UAV aeroplane measurements, they are only showing spontaneous flux. So usually they do not report K value for the landfills. They report this flux Q for the landfill site. So we call them QR, reported Q, and consider them as benchmarks, meaning the most accurate values for some of the landfills, right? So this is Q is basically a flux with the unit of what? Volume of methane per time, usually per day. So cubic meter per day. That is what they are reporting using the satellite and also the airplanes. So we also want to compare the fluxes with our estimations. So again, for these sites, here we have 32 such sites with satellite or airplane measurements. For these sites, we can also, get the site information, get the K value, and calculate the improved flux called QCMT. So it is the flux that we estimate using our improved approach called CMT approach, which the equation is shown here. And correspondingly, we can also calculate the flux using the default IPCC value for that site called QIPCC here, right? So you can see that, well, basically it's the same first order decay equation, just that we have 2 different K values here. K values, different. And then we take another small step to get the difference between QCMT and QR. Basically, the arrow of the QCMT calculation. Take this arrow as delta CMT. That is one of the axes on this figure. And then the other arrow, IPCC arrow, as the delta IPCC, also shown on this figure, right? So on the x-axis, we have this delta Q IPCC, meaning that if we use IPCC's method to estimate flux from this landfill, what's the arrow between the IPCC estimation and the satellite measurement? So this is x-axis, delta IPCC. Y-axis, similar idea, delta CMT. Our improved approach was the arrow, right? So then we are plotting these 2 together. Basically, we wanted to just show the comparison between our method and the IPCC method. And each point is, one site with these QCMT, QIPCC, and QR. All right. So let's just take one, it's still a bit, maybe not intuitive. So let's just take one of the points as an example. For example, this point here. Oh, wait, let me take actually a satellite point, which let's take one of the brown triangle point. Let's say, for example, this one here. By the way, I believe this is probably the Pakistan side, PK side. And from the Science Advanced paper, and also from Science Advanced, there is another Argentina site here, somewhere here, I guess. All right, let's look at this triangle, right? This triangle basically shows that if we use IPCC and compare that with the real measurement, the arrow is, and by the way, this arrow is in a percentage. Oh, sorry, we need to divide this difference by the QR. I forgot to put this. So this arrow is in percent. Then IPCC's estimation compared with real measurement, the arrow is around 50%, a bit more than 50%, right? If we use our approach, the improved approach to estimate methane emission from this site compared with satellite data, the arrow, there is still an arrow, but much lower, right? You can see around 15%, 0.15. That is our arrow versus their arrow, IPCC arrow, let's say 0.55, right? So this is just one point showing that indeed our approach is better. We have a smaller arrow, lower arrow. And then we just keep doing this for all these sites with satellite or airplane data. And we see that most of the data are below this one-to-one line. Again, this one-to-one line means that the arrow of our approach and IPCC approach is the same. But here we are basically showing that, our arrows are in general lower than IPCC's arrows. In other words, our approach is closer to the real measurements. Our approach is more accurate than IPCC's default approach. All right, so that is basically two-step verification, and that's all the verification we can think of. So that is basically the end of the verification step. But one thing I do want to add on is if you look at this arrow distribution on the side, right? Our arrow distribution is accumulated or concentrated towards the lower end, somewhere here, right? Whereas IPCC's arrow is somewhat higher, right? So that also shows that, our approach is better. So basically, we try a few ways to try to convince people that our approach is better, more accurate. So that is kind of the end of the story. This is actually the last slide I want to show. Is now we are pretty confident with our approach, the K improved estimation approach called KCMT, right? Then we think, okay, what else can we do or what else can we calculate to basically show people that this is a real or major problem, the underestimated K value or the wrong K value from the IPCC guideline, right? Then we extend or extrapolate our case. Well, first we select 10 major landfills and dump sites globally, those without measurements or with some of the site information. So we basically select, major landfills and dump sites worldwide, including Shanghai and Guangzhou. Shanghai, there's a Laogang landfill. I think some of you may know that. And then we pick Jakarta because, it has a high population and high waste generation. Mumbai, India, obviously has a major open dump site. I think it's called Gawadipur or something. It's a very famous, huge dump site. And then we also pick dump sites from different countries, different continents, basically, different climate zones, Peru, Brazil, and also London, and a few 3 sites from the United States, right? So we pick these huge sites or big sites with available site information. Then what we did is to predict their methane emissions using 2 methods. One is the default IPCC method, and the other one is our improved KCMT value, right? So we can use these 2 different K values to estimate cumulative methane emission from these sites. And what we see here is that well, I'm not going to pick a single site, but you see that all these orange lines, meaning our estimations, are much higher than the blue lines. The blue lines are the IPCC estimations. So what does this mean? In other words, this means that most of the sites, the methane emission from at least from these sites, are underestimated. And our approach, our estimation, basically raised the number, right? Then people will ask, what's the matter? Why you want to show a high number? Well, this is basically we need precise numbers. Then we can think about how to mitigate. and then target the landfills to reduce methane emission, right? So this basically sets the stage for future research and future policy and etc. So that's what we consider as our major contribution from this paper. All right, so that's all for my presentation today. The last slide, I just want to first show my contact method, email and WeChat, and then also to let you, just want to let you know that recently we are publishing or discussing, publishing quite a few papers on solid waste management. So if you are interested, you can check these out. Thank you very much for listening.
Yeah, thank you, Professor Fay. Excellent lecture. I really like your way of explaining. It's very clear and very detailed, and I also like the way you use the marker, on the screen. So that way we can follow what you're talking about. It's very, very nice presentation, and very nice way you presented, so that we can understand it, and a very impactful research. I hope IPCC would use your results and maybe revise their recommendations going into the future. So very, very impactful research. And I know everybody is worried about climate change, and climate change is due to these greenhouse gases. Methane is one big issue. So we need to get a handle on that one. So it's very nice presentation. And anybody who is interested in looking, or anybody looking for a hot topic to do research on, is like a methane is a hot topic, I would say. So
Right.
first order of business, I would say, if you have any questions, put it in the chat box. Before we